Okay folks, welcome to Printed Circuit Board Design Part 1. We're going to be talking about schematics and how to build parts in the Eagle Electronic Design Assistant software. Now, the electronic design process starts with a concept. What do we want to build? In this case, we're going to be working with an RGB LED grid module that we're going to be putting together, right? So we have some kind of idea that we want to build and an idea about how to implement it. The next step is analysis and prototyping. This is where we look up the parts we want to use, we breadboard it out, we prove that the circuit works before we start to capture it in a fixed format. The next part is the schematic capture. Once we have it worked out sort of on a breadboard and prototyped, we can put it into a piece of software that allows us to represent it graphically and also allows us to do analysis on it. There's a bunch of different kinds of software that allow us to do this. Most basically, we have some schematic software which is just for drawing. More advanced pieces of software like PSpice allow us to do actual electrical simulation and determine how transient behaviors of the circuit are going to work or anything like that. This piece of software we're going to be using is halfway in between. It allows us to do a graphical representation of a schematic and then transfer that into and allow us to do some basic analysis on whether things are connected right or if there's any dangling circuits or anything like that, which is called electrical rule check, which is the ERC part in this diagram here. Then once we have a verified schematic, we can move into layout. And this is where we actually lay out the parts on what will become our printed circuit board. We determine where the wires are going to go, where the parts are going to be laid out, and we can do what's called a DRC, which is a design rule check, to make sure that parts aren't overlapping and that wires don't cross too close to each other and all kinds of stuff like that. Once the DRC is passed, once the design rule check is passed, and we know that what we have should work, we're going to pass it off to manufacturing, and they'll actually build us a board representing whatever printed circuit that we designed. Then, once we get that board back, we populate it with components, solder everything to it, and then we can test it and see if everything works out, right? So what's going to happen in this video is that we're going to do this first part, which is the schematic capture using CADSoft Eagle. So this assumes that we have a circuit that we've already prototyped, we've verified that it works, we've done the breadboarding, all that kind of stuff, and we're ready to capture that schematic in the CADSoft Eagle software. We're also going to look at creating new parts in Eagle and what that involves and do an electrical rule check. Videos that follow this will do the printed circuit board layout and the design rule check. So, first step, if you're going to be doing this, is to go to cadsoftusa.com and download the Eagle electronic design software. And when you're installing it, it's going to run. We want to choose Run as freeware. For educational purposes, it's free, which means no commercial use, and we have some limitations, mainly that the printed circuit board that we produce can't be bigger than 10 centimeters by 8 centimeters, which is pretty big for most small projects. We're not going to be designing motherboards or anything like that most of the time. So it's pretty good, and it's really excellent software. I like it a lot. There are other options out there that are free and unlimited, such as KiCad, which is currently under strong development by CERN. A lot of the concepts that we use here are going to be directly applicable to KiCad, so you can use that if you want, but I find that Eagle is a little bit easier to use and a little bit less confusing, so that's what we're going to go with today. So our design example, first we're going to gather some data sheets, right? So we want to look at all the different kind of parts that we're going to be using. I've got this 8x8 LED grid, I've got a Maxim LED driver, some headers, capacitors, stuff like that. Whatever I need to support the actual physical device. Now, I need to gather data sheets for every single one of these parts because I need to know not only how they're hooked up electrically, but what they look like physically, because we're going to be building a physical board. The mechanical portion of it is super important, right? And before this, I'm assuming that we have some kind of draft of the schematic on paper, or I have an idea of how everything is connected. I can be looking at my breadboard or something like that directly and building the schematic from that, right? So let's move on to starting a schematic. So when we first start Eagle, this is the screen we see, and this is where we can start new projects, new schematics, boards, and all kinds of things like that. So we're going to start a new schematic here, and what we have is a schematic drawing area, and I've also collected all the data sheets and information I'm going to need to build this board, including the LED driver, and this is the LED grid itself, and everything that I need to know about the circuit. So we're going to start off with this circuit which supports the LED driver. So the first thing we're going to do is add some parts to the diagram, to the schematic. And there's tons of stuff in the part library that's available. So we can start with the the Maxim products and find the specific part that we're looking for. So here's Maxim, and I'm going to scroll way down to find the LED driver. Here's the LED driver that I'm looking for, and I'm going to make sure that it's the exact same package, so it can come in through hole or surface mount. This is the right one for me, so we're going to hit OK, and that allows me to place it on my schematic. And I'm going to place it pretty close to the origin, that little plus sign, because that'll help it make it easy to find later. Right, so then once I've placed one down, I hit Escape, which takes me back to the Add part. And I'm going to add some of the support electronics. So I'm going to need a resistor, and I'm going to need a capacitor, a couple of capacitors. Those aren't in the schematic, but they're smart for that. The next thing I'm going to add is the connector, which is a 5-pin connector. It's in the CON LSTB, which is just generic. And I'm looking for the 5-pin, and there's all kinds of configurations here. The 5-pin header here. And this will be how I connect to the outside world. So I hit OK. Drop it down, and you'll notice that when I drop it, the name and value are replaced with specifics. It automatically increments part numbers and things like that, which is really nice. Next, I'm going to look for a capacitor, I believe. Go to the generic RCL, and there's a couple of versions. There's US capacitors and there's European capacitors. I'm going to go for the US capacitor. I want the polarized version for one of these. So I'm going to look for the size. Now this is where I'm trying to match up the specific physical mechanical format. And there's a bunch of surface mount ones at the top. I'm looking for a through hole one that's going to be Panasonic style. Alright, so here's one, and I need to verify that it's the right size. So I'm going to look at my data sheet over here on in my browser, and this is the capacitor I want to use. This is the electrolytic polarized one, and I want to make sure that the lead spacing, the wire spacing, matches what's in the diagram. So if I look at the description and the diagram there, I can see that the lead spacing is 2.54 millimeters, which is exactly what I want. So I hit OK, and even the schematic symbol hasn't changed. The physical representation of that, what's going to actually show up on my printed circuit board, has changed, and I want to match that. So I drop down one of those, and next I'm going to do a non-polarized ceramic version. I'm going to use the European symbol instead because I think that makes a little bit more sense. So here's one, and I'm going to go and double check again the physical format of this thing. And it looks like the size is, yeah, my lead spacing is about 2.5 millimeters again, which looks great. And I can drop that guy down on the diagram, and it'll be awesome. You can see both of them. The first one is C1 and the second one is C2, which works out really nicely. Then I want to add a resistor, and again I'm looking for the physical format of the resistor. In this one, the lead spacing varies a lot, so I need to make sure that I check my part, again the physical part that I've ordered, and make sure that it matches. So I want it to lay flat on the board, so I'm going to look at the size. It looks like it's just over 5 millimeters long, so I want to use a format, I want to use a footprint that matches that size, that allows it to lay down. Right, so I'm looking at the sizes here. There's a 7.5, that should work great. Now, to rotate it there, what I did was right-click while I had the part, and that when I right-click, that rotates it 90 degrees, which is super handy. Next, we're going to add the power and ground symbols to the schematic. And to do this, I go and find the supply library in Eagle, and I'm going to pick a 5-volt supply object and drop that on the schematic. And I'm actually going to drop 2 of these. One for the header and one for the power for the chip itself. Now, when I put these on the diagram, they're going to be connected directly between the two in physical reality. So even though they're separate in the schematic, they're actually going to be connected by wires on the board itself, which is a really handy thing. It helps us keep the diagram clean. And I put a ground symbol there too, so I've got a 5-volt bus and a ground bus, and anytime I use those signals, those are going to be physically connected together. So now that we have all the parts together, we're going to need to add the values to them. We need to set what value they are so that when generating our bill of materials, we can use the right ones, right? So here I use the value tool, and I just click on each of the objects and I set whatever their value is. So it's a 10 kilo ohm resistor, 0.1 capacitor, 10 microfarad capacitor, things like that. So now that I have all the part values set, I can start connecting them together using the wire tool. We're going to start with the connector, and what we're going to do is basically just following the schematic, we're going to connect them together. So all I do is click and once on a pin, and that starts a wire there. And when I click again, it makes another connection to a pin. Double clicking will stop it on a pin, and hitting escape will also stop the wire from following you around. And you can see every time I click, I can make little bends in the wire, and just kind of drawing around and making these electrical connections. So that finishes up my connector there, and next I'm going to start moving some of these around to kind of clean up the schematic, the area where the power filtering goes, and make sure that everything is laid out in a way where I can run wires between them and it's easy to read. I don't want wires overlapping. I don't want wires overlapping the names of the objects or anything like that, so that the schematic again is easy to read. I can reference it later and make sure that it's a good representation of the circuit and it's easy to read. Fast forwarding a little bit here, I'm almost done with the power filtering circuit on this side here, right? And I've got a bunch of wires all kind of connected around, and the thing is, some of these wires cross or meet at a join, and they're without this little junction tool, these little dots that I'm putting down, they're not actually electrically connected. If there's more than one wire at a point that meets, I have to make sure I put this junction down, and what that does is flatten the diagram. It actually makes those wires connect. So now that most of my schematic wiring is done, I want to do a little bit of cleanup, right? So what I'd really like to do is to move that header in a little bit. It's kind of sticking out. Now I can just move the component, but it doesn't move all the things connected to it. So I'm going to use the group tool to highlight a whole bunch of stuff. And you can see once I've selected it, the move tool is automatically selected. So I'm going to hold down Control, then right click, and I can move the whole group at once, which is really nice. So next we want to add the connections to the LED grid to all those over there. Now I'd check the library section, but there isn't a part that matches this. So we're going to have to create our own part in this case. To do this, we're going to go back to the main diagram and start a new library. Inside the library, I'm going to start a new symbol to start off with, and this symbol is going to represent the component in the schematic diagram. There's going to be 3 parts to this. We're going to create a symbol, we're going to create a package, and then we're going to create a device that links to two. So the first thing we do in the symbol editor is we're just going to draw an outline of the LED grid, and we kind of want it to look like how it's represented in the data sheet so that it matches up really well, right? So the first thing we do is we're going to draw an outline of the entire object. And I'm just going to make a big square here going all the way around, and I'm going to do some counting to make sure it's the right number and I know that I can put pins down in the right places. So now that I've got my big square, I'm going to use the group tool and move to center the outline of the object on the little plus there. That's the center of the object, and that's typically where we want to put the anchor. That's where we're going to move any parts that are on there, so we want to make sure that the outline is centered on that. Then we're going to start using the pin tool. Now the pin tool allows us to place pins down in the diagram, and the little green circle is where wires will be connected to things on the outside. And I want to match the numbering of the pins on the diagram here. So this is not how they're physically wired, but this is how they're wired on the schematic, and it's going to make a lot more sense. So I'm going to put a bunch of these down in a lot of different places, and it looks like they're going kind of all over the place, but every pin I put down is in order. So pin 1 is actually in the middle of the left side of the diagram, then pin 2 is a little bit farther down, then pin 3 and pin 4, and so on and so forth. So I'm going to kind of jump all around here because I'm trying to follow what the data sheet looks like, and that's going to make logical sense rather than physical sense, right? The physical part will come when we match this to the footprint of the device when we finish the schematic, because we have to put the footprint, which is where the physical pins are located, down later, and then we'll link up how the schematic gets translated to the physical footprint. Skipping ahead, I'm done laying out the pins, and the next thing we want to add to the schematic symbol is the name. Now, it's not the name tool. We're actually going to use the text field and use a specially formatted text thing. So I'm going to use a left open caret and type name, and anytime I place this down on the diagram, the eagle is automatically going to replace it with whatever the part name is. And I'm also going to do the same thing using value, and value will also get replaced. So for example, when we do capacitors and stuff like that, when it automatically names them C1, C2, and C3, this is the field that's getting populated, right? So I put down the name and the value in different places. Usually it's on the outside of the diagram somewhere. Next, we're going to create the footprint. To do this, we're going to select New Package and give it a name. And what this is going to be the physical representation of how the pads for this object, how the wiring connections for this object are going to be situated on the board itself. Now, since we're doing mechanical design, we want to take advantage of a really regular grid grouping so we can make sure we put our pins down in a measured way, right? It has to fit the diagram layout of the board has to match the physical layout of the pins themselves. So what I'm doing here is setting the major and minor grid points so that when I put down pads to match the diagram in the data sheet, I can make sure that those pads are exactly spaced the right way. And we can see that from the diagram that they're spaced about 0.1 inches from each other, which matches the breadboard spacing, and they are laid out about 1.1 inches away from each other in 2 rows. So I'm zooming in way here to make sure that I get down to my basic grid thing, and I can start putting down pads. Right? I can pick from a bunch of different pad shapes. I'm going to pick sort of an oval shape so that I can pack them in close to each other and make sure that they're rotated so that they're in a right orientation and go side to side. And I'm going to put these down in order, and note that the first pad on the bottom row is on the left, and then I'm going to drop it down, move over 0.1 inches, drop down another pad, move over 0.1 inches, so on and so forth, and I'm going to do one whole row that way. Then I'm going to go up to the top and go the opposite direction from right to left instead of left to right, because that's the way that the pad numbering goes. So here I go, putting down numbered pads, 1, 2, 3, 4, 5, 6, all the way across 8 pads. So next I'm going to zoom out here to make some room to put the other pads in. And I'm going to start off by selecting the pad tool again, then counting up until I get far enough away. Remembering that my grid is set at 0.1 marks, I count up until I get to 1.1 inches, then I can start putting pads down from right to left instead of left to right so that they're in the same order. Remember, the pad numbers are incrementing all by themselves. So now that all the pads are down, what we want to do is add a some documentation, something that's going to show up on the printed circuit board to tell us where the physical limits of the part is. And what we do is we call this a part outline. So I pick the wire tool, and in this case I'm actually using a layer that's just for documentation. So when I did that pull down menu up at the top where it says TDocu, this is where the part is actually going to go, and this is going to be drawn on the board, and it's going to be visible when we're doing our layout. I did some calculations here to make sure that where I'm putting these lines actually matches the physical location, the physical outline of the part itself. And what this is going to do is it's going to help us make sure that when we're laying out our printed circuit board, we don't put any components too close to this LED display so that either they end up under it or on the edge or anything like that, because we're going to be assembling it and we don't want them to overlap. That's bad form, right? So there we finished the diagram. It's just a little bit out of whack, so we're going to make some adjustments here, and that looks pretty good. That looks pretty close to what the diagram should be. Next, we want to do the same thing that we did for the schematic and add the name and value text fields. And this is going to help us when we're trying to figure out which part this is when we're putting it on the layout and when we're actually assembling it. So I'm going to put the name somewhere in the diagram. It can go on the inside, it can go on the outside. We're pretty much going to use it only during assembly, so it can pretty easily be covered up. If you want to use it during debugging after it's been assembled, maybe you want to put it outside of the diagram like I did here. But value for sure is going to be something like a part number or something like that, so it doesn't really matter too much if that one's covered up. Now that we've finished the footprint, we can create a new device that connects our schematic object to our footprint object. So that's what I did there. I selected the new device. I'm going to give it a name. We're going to save it, and it's going to take us to a new window, a new editor that allows us to put down a schematic object. So I'm going to add a schematic object, then and make sure that that's centered on the plus sign. So that make sure that the anchors basically line up, which is nice and clean there. Then I'm going to add a footprint object, our device, our package to it by clicking there, make sure it's the right one. Then all that's left is to connect the two. So I have a connection error there, and basically what we're doing here is connecting from a pin that's on the schematic to a pin that is on the package. And since we put them down in the right order, all I have to do is match 1 to 1, 2 to 2, 3 to 3, 4 to 4, stuff like that. But depending on how our package works, we could have multiple packages for a particular schematic and things like that. So once I save that, that basically creates our own library. And to use it, we're not going to be able to yet find it in our library menu. Our My Library object hasn't shown up yet. So what we have to do first is to go back into Eagle and add it. So what we're going to do is going to go to the library, click Use, and then we're going to find our My Library object. And it could be whatever name you want to do it. Usually we group it by manufacturer. Now that should show up in the Add Device menu, and all we have to do is find it, select the one object that's there. There's our schematic and our layout. We could plop it down on the diagram, and it's a little bit big. So I'm going to skip ahead here. We're going to shrink this thing down and do a little bit of editing, but basically it just goes back through the same process that we did before. So here's our new schematic object, and you can see that I've shrunk it down quite a bit and compressed the pins together. It matches the rest of the diagram a little bit better. And I've also renamed the pins. Now this didn't change the pin names, it just changed what's displayed in the schematic, which it makes it a lot easier to read and a lot easier to understand. So what we can do now is start hooking things up, and I've got about 16 wires to make. Now this is going to get really messy. You can kind of see here in a hurry. If I go 1 to 1 for all the rows here, I'm going to have a lot of wires on the diagram, and when I start to connect the columns, things are going to get out of control. I'm going to have a lot of wires crossing, or I'm going to have to go way around the other side of the diagram. Now, to make this easy, Eagle has a really cool tool called labeled buses. So basically what's going to happen, what I can do is I can make a bunch of little stub wires and give them names, and if I name two of the wires the same thing, they're going to be connected electrically even though the connection is not actually made on the diagram. So here I'm going to make a whole bunch of little stubs, and I'm going to fast forward here to once I'm done with the stubs, and then we're going to label them, and connect them all together so that they end up being really clear and connected. So now that I've got all my little stub wires on the diagram, I'm going to use the label tool to make the name of the wires show up. And initially it's going to be some like $N, and this is Eagle's internal representation of the name of wires. It stands for nets, right? So then once I have got that label displayed, I can change the name of the wire, and then I can use the name tool to do the same thing. And once I give them both the same name, they're electrically connected. So now that I've finished naming all the nets and making sure they're connected, it's time for the last step, which is our electrical rule check. Now what this is going to do is it's going to check to make sure that all of the wires are connected, that all the pins that are important are connected, and things like that. So all I have to do simply is go to the menu up there, do electrical rule check, and it'll give me a list of possible errors. And really most of them are just warnings unless something is really wrong. And in both of these cases they're super minor things, so all I have to do is approve them, but Eagle will highlight where the problem is, and you have an opportunity to fix it. Now that that's done, that's the last step. We have a final schematic, and it should be ready to be transferred into a printed circuit board.